The next speaker is Oliver Blume, who is a research manager in Nokia Bell Labs in Stuttgart. He's the leader of a research team on mobile network performance, low latency, and high reliability for Industry 4.0 cases and machine type communication. He also has been driven a number of major projects, external projects like Project Earth, Green Touch as well. That he will talk about this in his presentation in a few minutes, but also internally with the Nokia Future Cell project that I also give some details in the previous training school that we held in PAINLESS. And last but not least, he was also the manager who hired me in the first place when I joined Bell Labs. So without further ado, I give the microphone to Oliver, and also the presentation right. Okay. Just 1 second.
Okay.
And yeah, the floor is yours.
Okay, so I can start sharing. I've received the ball, and I will go to presentation mode to go to full screen. Oh, I hope you can hear me and can see my slide now.
Yes, not the slide now. Yes, and
okay,
it's good.
Yeah. So thanks for the opportunity here to present this work that I've been doing some years ago. Lorenzo mentioned that I'm now working on more networks, vertical application networks. But before that, I've been dealing with energy efficiency quite a while in several research projects, namely Earth and Green Touch, and I will come to the results of this and take you through a journey through the work that we did here. That basically started in 2009, when there was massive research activity for energy efficiency, with the bulk of the work done in the years 2010 to 2015. And I want to take you through the findings that we had in this time and the breakthrough methodology, so to enable you to follow this conceptual work and then apply it to your work for 5G and the next decade of research. So the structure of my presentation is first with a short introduction into energy efficiency on a high level. Then we will deal into why we as telecommunication engineers should care for energy efficiency. Then we will take the view of an operator asking how green is my network, to understand how it compares to the energy efficiency of other networks and what the bottlenecks are for energy efficiency and where the gain could be for saving energy. So we will then dig into more deeply into the technologies, what we can do to analyze the energy efficiency and then to use mitigation strategies and technologies. And I will conclude then with a call for action for you. So first part is energy efficiency, and it seems very natural for us in these days to talk about energy efficiency. But I want to challenge you. Have you ever thought about how old this concept actually is and who introduced a view of energy efficiency? I will offer you 4 choices here. The first one is a guy named Hans Carl von Carlowitz, and he worked in sustainable yield forestry and actually founded this work back in 1713. The second choice is Nicolas Carnot, which is well known for his work in the efficiency of generating mechanical energy from heat in combustion engines of steam engines. That was done 1824. My third choice is Wilhelm Ostwald. He's a chemist and was studying dissociation energy in chemical reactions. And he also coined the chemical unit mole. And he worked on this in 1819 in his book called Die Energie, or The Energy. And the final choice for you is Donella Meadows. She was the lead author of the famous report of the Club of Rome with the title The Limits of Growth in 1972. And showing that economic growth would not be infinite because of resource depletion. So with these 4 persons here and 4 different times in history, what do you think actually when energy efficiency was introduced as a term? I'll pause for a moment to let you make up your mind before we proceed then with the details and the resolution. So maybe you have taken your choice, and I will take you through the aspects of the term energy efficiency. And you will see that this has different aspects, and it also relates to the people, basically to all of the people that I was giving you for the choice. So the first aspect is the availability of resources. And so this clearly associates to Karlowitz, who coined the term sustainability, introducing the idea that you can only take as much wood from a forest as is growing again. And of course, also this relates to the Club of Rome, indicating to the limitation of resources. So these are economic issues in availability of the resources. A second aspect is then the limitations that come from physics for the achievable output that you can have, and that is what Carnot was introducing, the efficiency of an engine, how much useful work you can take out of a machine. So this relates to the second law of thermodynamics and the limits of conversion of energy. And this clearly is an economic issue because it defines the cost that you have for energy doing your work. The third aspect then is a bit newer, and that is waste and pollution. So every use of fossil energy will produce dust, carbon dioxide, NOx, and these are hazardous materials both for human health and also for the climate, as we in very recent time have experienced. So these are ecological issues, which in the end also may turn into cost by taxing for carbon dioxide, for example. And I want to add a fourth aspect here on the plus side. So saving energy, so spending energy is not always bad. In fact, it can be productive to spend energy to save more energy in other places. This is called abatement potential or leveraging effect. And a very good example for that is what we are doing right now. So we are in a video conference. We are spending energy on the servers and on the transmission of these video through the network. So that clearly is a cost of energy. But at the same time, we have saved the energy for traveling to London, unfortunately, I would say. But from the energy perspective, this is a lot of saving that we are taking here. And it has been estimated that information and communication technology have an abatement potential of actually tenfold. So every joule spent in communication has the potential to save 10 joule for physical work. And now back to the question, which of the 4 guys actually coined the term energy efficiency? And the correct answer is all of these aspects that I was presenting, economic, ecological, and even the leveraging aspect, was embraced by Oswald in 1819. So I guess none of you will ever have heard his name. I will take you to a short introduction of Wilhelm Ostwald. He is a pioneer of chemistry, working on catalytic reactions and the speed of chemical reactions, so studying the energy associated to dissociation of molecules. And he's also a Nobel Prize winner for chemistry in 1909. A bit earlier than that, around 1819, he was also taking the philosophical approach to energy and introducing energy as a concept into physics and chemistry. And while working with this, he realized that it's not about just the chemical reaction, but in general, on a large scale, the budget that we have for spending energy on Earth is limited by the resources of Earth. So this led him to adapt Kant's categorical imperative into something he called the energetic imperative. And he was understanding that it is a general task of all human culture to make sure that we are not wasting energy. I give you the original quote here in German from one of his later work. So he was actually coining this term of energy efficiency and bringing it to awareness. By the way, he also had a second really breakthrough vision in our field and related to this talk, and that is harvesting energy. So already in 1911, he was dreaming of harvesting energy directly from sun as a main industrial source. And this was 40 years before Bell Labs ever demonstrated a first practical and working prototype of a solar cell. So with these two concepts, Oswald was really a breakthrough in this area. And I would land on the picture that Laius was painting with the stroll taking following Shannon on the way to 5G. So I would like to have Oswald gain us through the energy efficiency work in this presentation. So what happened since, fast forwarding 130 years from this Oswald realizing the importance of energy efficiency. And using the Gardner hype cycle, I would see it has been quite up and down in the work for energy and the relevance of energy efficiency. This original interest at the beginning of the 20th century faded away, and energy efficiency was not a main topic. It was more about bringing new ideas and inventions, not caring so much about the energy. And that did not change until we ran into a crisis, and this was the oil crisis in the 1970s and 1980s, when suddenly fossil fuels were scarce, and we could not use energy in the way that we used to do. So this forced us to look back into energy efficiency and start to work on energy saving. But as you could expect, as soon as oil was largely available again in the 80s, interest of energy efficiency faded away and did not play a major role in driving technology. Until we ran into a new crisis, and that is the climate crisis. I would assign to this the time frame 1990 to 2010, when really scientists came to the conclusion that human activities in spending energy have a devastating effect on the climate. And this culminated, say, in 2010 in the UN running the Intergovernmental Panel of Climate and the Copenhagen event for agreeing on protection of the climate with limiting the temperature rise to 2 degrees. But as you all know, this undertaking in Copenhagen failed. There was no binding resolution how to save energy and how to act on energy efficiency. So this also faded down, but not without having a massive impact on research for telecommunication. So this peak of expectation here for energy efficiency triggered the work on energy efficiency that I will report today, starting in 2009 and lasting 2010 to 2015. With the completion of this work, I felt that the awareness of energy efficiency was again fading away in a third trough of disillusionment, and it was not really taken to market and to adaptation. I was expecting at that time that it would be rising cost of energy and also cost of carbon taxation that would finally bring energy efficiency to application in our field. But maybe I overlooked some other aspects that right now have brought back energy efficiency to this awareness. And I feel that within the last few months, from many different directions, I have been approached for recalling the work that we have been doing on energy efficiency. And I would say now that this is triggered by two events that I picture here with the famous picture of Greta Thunberg in the UN when she was delivering her "How dare you" speech about energy consumption and climate crisis. And very recently also I would add another thing, and that's the crisis, the Corona crisis. How is that related? The Corona crisis has taught us how important communication networks are actually for running our economy and running our daily life. And within a few months, the consumption of data volume in the networks has jumped up in a way that usually we would see on the order of 1 or 2 years. So this brings network and telecommunication to the core of the attention again. So summing up, this means we have 4 drivers for energy efficiency in telecommunication. It's the tough market situation with high cost for the operators for the energy. It's the increasing use of the network with also new services in 5G and Internet of Things. It's sometimes the limited availability of energy, and this is where PAINLESS is very related in having off-grid locations for base stations. And finally, I would also say that it's a competitive edge for network operators to have a green renommee and a green tag to their branding, not to mention regulation that can enforce green behavior of network operators. So that clearly brings us to the point that energy consumption should be and has been an important issue for telecommunication engineers. Mainly triggered by the awareness of rapidly growing data rates over the years. So why is that an issue for the operators? I mentioned the cost. You know that mobile communication used to be a gold mine. Now it's a tight market where the operators are under huge cost pressure. And even at the time when we started this work in 2009, it was a huge cost driver for the operators. So if you look at these numbers in the upper right, upper left here, you can see that on the order of 4 terawatt, which translates to 1 billion of euros per year, is the power consumption of large operators, let's say in Italy or US or Japan, which sometimes is translating into several percent of the national energy consumption. Overall, ICT communication is said to consume 6% of the global produced electrical energy. So if that was back in 2009, we are seeing this annual doubling of data volume over time, here plotted with a prediction at that time for 2013. Today, we know that this is not stopping. This growth has slowed a bit, and in the latest numbers of Cisco, we have a compound annual growth rate of data volume by still 50% per year. So from 2010 to 2020, within this decade, we have seen a 200-fold growth of data rate. So what's that doing to the energy bill and the rollout of new technologies like 4G and 5G? Here's a sketch of the OPEX cost, how that breaks down for network operators. And you can see that this has large aspects for site leasing and backhaul line leasing, for the operation and maintenance, for the network infrastructure planning and deployment. But the largest part of it is actually power consumption. So for an operator, it's a real big pain, to cite your project name PAINLESS, a real big pain if energy consumption is increasing and the cost of this is growing. So Nokia, or at that time it was Alcatel-Lucent Bell Labs, was looking at the projection of these costs for communication industry for both wireline and wireless communication. And we can see that it was predicting that if we are not doing anything about it, the cost of the spend of energy and related to that, the cost of energy would rise 8-fold until 2025, which clearly is not sustainable and cannot be accepted. So we have to do something about it. We cannot run business as usual by just introducing new technologies, not caring about the energy consumption. Rather, we need to strive for something that introduces energy efficient solutions that, in spite of the growth of the data rate, will enable us to have the energy consumption flattened out and even recurring, so that we can keep energy consumption at a reasonable level. So the question is, what technologies can we do and how do we apply them? It is well-cited fact that most of the energy is actually used in the radio access networks. About 80% is assigned to the base stations, and smaller, the remaining part then goes to the core network and the metro networks and other parts of the network. So why are base stations so power hungry? So let's look back at the time, say at the introduction of LTE. What was the state of the art at that time? Why are base stations so power hungry? A base station usually would come with an antenna mast with 3 sectorized or antennas, and each of these antennas is radiating 20 watt of RF power. To generate this RF power, we need power amplifiers, and the efficiency of these power amplifiers was as low as 12% at that point in time. Unfortunately, on top of that, 50% of the generated RF power is lost in the coaxial feeder cable that runs from the baseband compartment with the coaxial cable up the antenna mast to the antennas. So taking this together, to generate the 60 watt of RF power, we need 1000 watt of grid power for the power amplifier. On top of that, we have the signal processing and the platform power conversion inside the rack, adding up another 300 watt to the 1000 watt. So we need air condition with a chiller to remove this excess heat from the base station, with around 200 watt of power needed for the air condition. Summing it up, we have 1500 watt taking from the grid for the base station to produce only 60 watt of RF power. So this clearly has a lot of potential for improvement. And when we did this work, we quickly identified several potential and areas for the improvement. So sketching this picture as a roadmap for 2015, we have identified the opportunities. First one, obviously, is to get rid of the feeder cable. And that is the technology of remote radio head that allows to bring the power transmitter, power amplifier close to the antennas on top of the antenna mast, and having a backhaul, a front haul line connecting the power amplifier and to the rack. The second part is 12% efficiency of the power amplifier definitely is not the end of the technology possibilities. So it has been possible to bring up this efficiency to 40% in the end using gallium nitride power amplifiers, for example, and amplifier architectures. So this reduces the power needed for the transceiver to 150 watts. We also benefit from Moore's law for the signal processing, the semiconductor roadmap, bringing down every year the energy consumption of chip consumption for digital signal processing, for example. So that adds another part. It allows us to get rid of the chiller and run the cooling of the base station rack only with fans, passive fans with low consumption of 20 watts. Altogether, this brings down the energy consumption by a factor of 5, and now having 20% of efficiency of grid power into RF power. But that should not be the end of the story. We need to go further on. I would call this business as usual, benefiting from Moore's law in the electronics and taking these architectural changes like using remote radio heads for reducing. We can do more, and this is what we analyzed. What additional potential do we have? I quickly want to add on the other parts. I said 80% is done in the radio access network. We also have other areas where a lot of energy is used. Let's start from the core network with the data centers. So these are huge server farms running the applications and running the core network functions of the mobile network. And here, power saving is about using renewable energies, reducing the power efficiency for the cooling. So very different technologies and very few sites that need to be cared and addressed. A very different market. I was already explaining that the access network with around 10 million base stations around the world today is a massive contribution to the power consumption and to the energy bill. Yet again, a very different market is mobile devices. So this is a very fast market. While the access network, this equipment is brought to the field to be there in place for, say, 10 years, with little change that you can take to the hardware. On the other hand, mobile devices, they have an innovation cycle of, say, 6 months. And a lot here is about the large display and about the battery lifetime. Going back for this time frame of, say, 5 years, the last 5 years, we've seen that the battery of mobile phones has doubled. Take, for example, iPhone 6 to iPhone 11. But still, we are talking about daily recharging of these devices. So energy efficiency of the devices here is clearly related to the uptime of the device. And yet another market with even higher mass market features is sensors brought to 5G networks, running on even lower power. And the target here is to allow that these elements can operate on a single battery without replacement for a 10-year lifetime. So from that, it is clear that these different parts of the network have extremely different market scaling and technology, and we cannot handle all of them together. But I would lend the imperative, the energetic imperative of Oswald here, that we must save energy, and everyone needs to look at its own realm and start saving energy. And the realm that I'm working in is access network. So this talk will be about the energy saving in the access networks, and not doing finger pointing to the other markets, how they behave. So what we need is an analysis how green a network is. That has the point that an operator would take, looking at the cost, how to cut into the cost, how to improve the network, and how it's competing with other network operators, benchmarking which network is more energy efficient than the other one. So how can we assess the energy of the network? And I will try to bring this in for misconceptions and then into a framework for assessment of energy efficiency. And the first misconception in these early days was what is the proper KPI, the proper metric that we can use to assess the energy efficiency. And usually this was assigned to the, like we do for the radio performance of devices and users, that is associated to the throughput, to the drop rate, and to cell edge performance per device or per base station. So the first take was, let's look at the power consumption per user or per base station. But I will show you here that this is not really a good approach to the KPIs here. Introducing an analogy here from cars or for television screens. If you compare a smart to a Mercedes, you will clearly see that the smart is way more energy saving, running on less than half of the energy that you need to drive with a Mercedes. And the same, obviously, here, the television screen Model 1 is using way less power than Model 2, so seems to be the better choice. But hold on, if you now look at the seats, the smart can only run with 2 people. There are 5 seats in the Mercedes. So dividing the power spent to move the Mercedes, you will find that per seat, per person, actually it is more efficient to run the Mercedes. And similar for the television screens, the larger screen has 4 times the size of the small screen, but is only using 2.5 times the energy consumption. So it's a much better consumer experience, worthwhile the additional energy. So the bottom line here is that if you want to look at energy efficiency, you always need to put into relation the achieved task or the performance or the user experience to the spent energy. And for mobile networks, naturally, then it's 2 different KPIs that we can look at. The first one is for coverage. When we roll out a new network, it's about the coverage. So we have to ask the question, how much power do I need to invest per square kilometer of coverage area? That's the aspect for rural areas, kilowatt per square kilometer. If you look into a dense urban markets, for example, it's clear you need to cover all this area. Coverage area is not a changing factor. What's changing here is the capacity. It's the data volume that you need to serve in this area. So for this, we need to look at the ratio of the power spent to the data rate, or the energy spent to the moved data volume. So that's joule per kilobit, or equivalently watt per kilobit per second. Please note that, strictly speaking, this unit is not an energy efficiency. It's the energy intensity, because it's the energy spent for the used bits. If you want to transfer this into energy efficiency, it's just the reciprocal, so pretty easy to compare, to translate these values. So we've solved the first conceptual approach, and that's the metrics. Let's look at a second misconception. I call this the fixed efficiency misconceptions. So I was introducing the worries of operators that when data rate is increasing rapidly, the energy consumption will simply follow linearly. But this misconception is assuming that the efficiency of the network, the energy efficiency of the network, is independent of the load and the capacity of the network. And this is not true. I will show this throughout my talk here. Mobile networks have a good economy of scale. So introducing higher data rates and higher nominal data rates will actually reduce or improve the energy efficiency of the networks. And Green Touch as a project has quantified this potential for the networks in a projection towards 2020. So many people started working on improving the energy efficiency and ran quickly into another misconception. I call this the total power misconception. So following what was done for the performance evaluation of networks in system-level simulations, for example, people were studying the spread of energy and the performance of radio frequency on the way from the antenna to the UE. And that was adapted also for the energy efficiency, searching for the absolute limit, the physical limit for energy efficiency. So looking at the spread of energy on the path loss, the path loss exponent is quite high. As you know, it's probably close to 4. It means the energy is diluting with the distance from the antenna with a fourth order of the distance. At the same time, the size of the cell scales with the square of the radius. So obviously, if you cut down the cells into smaller cells, so deploy more cells per square kilometer to cover the area, you will gain a lot, because the transmit power of the antenna can be reduced by the force power, while the number of cells is only increasing with the square of the radius. So this plots this green line here, and immediately tells you that when you want to build a network energy efficiently, you need to apply small cells. But this is a misconception. As I told you, for the base station, we have the power amplifier efficiency, and we have additional power used for the signal processing and running the platform. If we adapt that to this approach here and add just 10 watt of power per base station, the picture completely breaks. So we can see here that adding more cells clearly has a linear increase with this offset power of 10 watt, yielding a sweet spot here for the size of the cell, which is the lowest energy consumption. And this, with the numbers that I'm applying here, is a pretty large cell actually, because it means that a cell is covering 5 square kilometers. So a really large cell, which definitely is was not expected to be the most energy efficient solution. But of course, you will note that this sweet spot critical depends on the extra power that we put here per cell. So we need to understand the power model of the base stations to find the sweet spot. What is the optimum cell size? And finally, I turn to a fourth misconception, and that is looking at the nominal capacity of the base stations. It is pretty obvious that the load of the network is changing over the day, and we have used operator data to analyze this, and it turns out that during nighttime the traffic is 7 times lower than during the busy hour. And that is just the high-level view. If you dig into smaller time windows, usually 15 minutes are monitored in the networks, you will see that the traffic in a cell is very spiky. So even in the busyness hour, when the cell seems pretty busy here, there are a lot of times when there is actually no transmission ongoing. And then it follows a spike that drives the cell into congestion. That is the temporal aspect of the variation of the traffic. There's also a spatial aspect. So operators have analyzed their networks and have found that there's a large spread in the load of the cells, and very few cells are actually ever highly loaded. So Vodafone was giving numbers that only 5% of the sites ever reach 90% of utilization. On average, cells are only used by 30%. And a network operator will start to get nervous with the growth of traffic when a cell is loaded 60% on average, and will start upgrading the network and bringing additional capacity to this cell. So by designing the network energy efficiency towards the nominal power consumption with a basically flat power model for the base station, leaves large saving potential from the times and the areas where the network is actually lowly loaded, so we can adopt energy saving methods here. So taking these 4 misconceptions together, we have designed a framework to evaluate the energy efficiency of a network. At these times around 2010, there was existing specifications by ETSI how to measure and quantify the energy efficiency of base stations. So this is taking a single base station into the lab, no UEs, no channel models behind that, just measuring the energy efficiency at different load levels. So you can create then from that bottom up a power consumption model of a complete network. GSMA was also introducing a service for mobile energy efficiency, taking it top down by looking at the energy bill of an operator and then comparing between operators. And the observation here is that, of course, it depends really on the size of the country, on the topology of the country. Is this densely populated, or is this a very large country? Does it have mountains, and what's the climate? So these will be factors that change the energy efficiency of the network, and this MEE service was discounting for these effects to make network energy consumption comparable. But neither of these approaches actually allows an operator to understand where the energy is gurgled in the network and where saving potentials are. So what we undertook is to build a framework in simulation to simulate a whole countrywide network of an operator for the energy efficiency, so that the operator play with bringing out technologies, bringing out network designs, and finding then how that would affect the energy bill. And this approach is breaking down the network into different areas and then taking representative chunks of the network to study in detail the efficiency behavior, and then scale that into by weighted averages of these different snapshots into a large-scale energy consumption. And this idea and approach to break down the network into representative areas and study them in detail and aggregate to the whole network consumption was quickly adopted also for standardization, and ETSI came up with a standard in 2015, adopting this approach for measuring also the energy consumption of networks in the field and enabling the operator to find where the energy is spent. So the Earth project was first designing this energy efficiency framework called E3F. And it was presented in a seminal paper in Wireless Communication magazine in 2011, presenting this idea of detailed modeling of the radio performance, adding a power model for the energy model of a representative area, deriving energy efficiency metrics, and then scaling this to large scale by using these different snapshots and having a weighted average. It also revealed that low load situations, like you can see here in the in the left of these two plots here have a lot of potential of energy saving by adjusting the network to these low load situations. And it also shows that dense urban and sub-rural areas have very different metrics for the power efficiency here for the coverage metric. So definitely need to be studied one by one. We have then extended on this and much deepened the modeling of this framework within the Green Touch project. This was not a European funded project as the Earth project, but it was a privately sponsored activity of many big companies under the lead of Bell Labs. And we derived here a much more detailed view and scaled the power roadmap to 2020. So I will guide you through the icons of this model here shown in the upper right. Let's start with the traffic models. We've used the operators as part of Green Touch to analyze the traffic distribution. I already showed to you a view on the temporal change on the day-night cycle and also the weekend cycle. But also the spatial distribution of traffic is quite, sorry, that was a bit too fast. It's very diverse, and we have even in dense urban areas a spread of the data rate with the background traffic shown in yellow here. Then we have hot zones with much higher data consumed, and still smaller places, hot zones where very high data rates are consumed. So we need to model this in the deployment and separating out the network into dense urban, suburban, and rural areas, and finding the right deployment for each of these scenarios. We also have to take the trend. We have already repeatedly mentioned in this talk the doubling of data rate annually. So that means the network needs to be redimensioned and will be consuming more and more energy. Then the second aspect next to the traffic is the power model. There we are. The power model deriving a very detailed model of the power consumption in the base station, starting from the antenna, the power amplifier, the front end digital signal processing, and the whole resource management and management platform. And all these aspects need to be modeled in the load dependency and also in the trends by introducing new technology and innovation over the time. So this power model needs to scale from at that time 2010 up to today to 2020. All of that is brought together to take detailed simulations, system level simulations of the wireless access, and then extracting from that the energy consumption in the coverage and capacity metrics. Because we are introducing here small cells, for example, for the deployment in the hotspot areas, we are adding also a new dimension to the energy consumption, and that's the number of sites that the network is running. So we found that it is also necessary to model the backhaul, and we developed here a BPON network, a passive optical network for the metro and the long range connecting the RAN sites to the core network, and adding also this power budget to every base station site. I want to take you quickly into a few aspects of the traffic model. So I mentioned the four types of areas that we are taking as representative, and we analyzed the traffic demand from the population density in these areas, and also the amount of area that is covered by each of these areas. And you will find that dense urban areas are actually a very rare thing. Only 0.3% of a typical country is dense urban areas, while nearly 90% of the area is rural. And then, as we already heard from Federico, there are large areas that are sparsely inhabited and not even covered by the network. So we have to consider that also. Aggregating then population density and fraction of area leads to an interesting fact, and that means all these four types of areas contribute significantly, each nearly a quarter, to the total data rate in the network. So we analyzed the traffic then by the per user amount of traffic used in each of these areas. For dense urban area, for example, arriving at around 8 megabits per second per square kilometer in 2010, and scaling that up for 2020 with roughly a factor of 100 increase of traffic to 700 megabits per second needed to serve in 2020. This factor of 100 has proven to be a bit conservative. Actually, as I mentioned, it has been a factor of 200 in this time, but that is a pretty good guess that we have been using here for the modeling. So how do we know that this model makes sense, that it actually can serve as a reasonable measure of potential for the operator? For that, we have taken the effort to compare reported energy consumption in this state-of-the-art 2010 and compare it with our model. So we have taken a study of GSM for the 2010 power use by radio access networks, and they have found that around 50 terawatts per year are consumed in mobile networks in the radio access network. GreenTouch was not building a model, a worldwide model, but was focusing on what's called the Group 1 countries, and that's basically the Western world, the developed countries of North America, Western Europe, and Japan. So we had to estimate a bit the fraction of the this power spent here in the countries that we are covering in our modeling, and it should be around 25 to 30%. So that would yield 15 terawatt hours per year, relevant for our study. So we employed our framework to cover these Group 1 countries, leaving out 30% of the area for not covered by broadband networks. And we derived that 1 million LTE base stations will have to be deployed per operator, assuming that we have 4 operators in place. That means we have 4 million base stations covering these Group 1 countries, which is a pretty close to what GSMA was reporting. So we can take that this model can be applied, and then using simulation and the power model that we derived, we yield 25 terawatt hours per year for Group 1. So comparing that to the 15 terawatt, it's, I would call, a pretty good fit, comparing these two approaches between top-down and bottom-up. And we are not aiming for 100% agreement of these numbers, because we want to find the hotspots for the energy and the trends for energy saving. So this agreement between the numbers is reasonably good, and we can go with this model. Finally, I want to point to one number here. This 25 terawatt hours per year and the 1 million base station and the data rate that we were using here is summing up to 170 bits per joule as the energy spent per bit. This shows that the network in 2010, so this first rollout of LTE, is actually strongly coverage limited. The energy consumption here is more closely resembling rural areas than dense urban areas. And I will compare this to the numbers later for 2020. So that was an introduction for you for the framework and how we analyze the energy efficiency of complete national networks. And now the question is, what can we do to reduce the energy consumption? The first observation is that energy consumption of base stations is not very load dependent. It's pretty flat. So the power model that we have built for the 2010 deployed equipment, early LTE equipment, was showing that with the load varying between 0 and 100%, there's only a 50% increase in the power consumption. So even when the network is running idle, it is using more than half of the nominal power consumption. Why is that? And the most consuming part here is the blue part, and that's the power amplifier. To understand this behavior, the power amplifier is running at a bias voltage, supplying and defining the saturation power for the signal amplification. And because the signals have a peak to average ratio and is also varying with the load situation, we need to take a large back off of the operation point for the power. So the operation point actually is this point here with the signal then spreading in the linear regime of the power amplifier. But now when we are running at low load of the system, we are still using all this input power of the bias power of the power amplifiers. What we can do is we can reduce the bias voltage. That will of course kick back and reduce the saturation level of the output signal. But in times of low load, when we're using low modulation encoding schemes, which have low peak to average ratio, we can still support the required signals without going into saturation and degrading the signal quality. And that's what we applied here during the Earth project. We designed transceivers that allow multiple operation points adapting to the load situation. And during the Earth project, there was built a proof of concept, and you can see here the red line indicating the measurement of transceivers using multiple operation points visible in these steps here, where the power the power of the electrical input power is reduced in steps. Comparing to the starting point, we have clearly reduced the power consumption in low load, and this also has an additional effect on the cooling that gives implicit additional savings. So much linearizing and starting that the network follows the load. A second aspect here is that it's not just about low load. What about no load? I told you that the traffic is very bursty, but it turns out that due to the frame structure of LTE systems, there's actually no time where there's non-transmission. You can see that across the time frequency resources, there are the system channels and the pilot signals for channel measurements spread around the area. So even when there's no user at all, the power amplifier and the transceiver continuously need to transmit these reference signals. So the largest gap that we have here is two OFDM symbols, and that is 140 microsecond of interruption times. So the first approach is that we can use these very short time frames for discontinuous transmission called DTX modes. But it is a bit worrying still that 10% or even 20% of the resource blocks are used in this system even when there's no user data transported. So that brings a lot of energy consumption already in a 5 megahertz LTE system. Now, what's going to happen when we go to 5G, allowing carrier aggregation and a full bandwidth of 100 megahertz? So 20 times the bandwidth, that means 20 times the reference symbols and a lot of power consumption. So it was a task for 5G to avoid this situation and to add flexibility on the frame structure. And two things have happened here, or a few things have happened. The first one is the reference symbols have been moved towards the beginning of the frame structure, allowing larger gaps for discontinuous transmission. A second one is that we have added flexibility to the frame structure. This is called bandwidth part, allowing to operate parts of the bandwidth with other modulation encoding schemes and other pilot structures and frame structures. So we can adapt the network flexible and switch off part of the bandwidth and allow saving here. So 5G has picked up on these findings for the energy efficiency and done a good job in improving the frame structure for 5G. Yes, having said this frame structure with the short DTX, we can take more sleep modes, and this is a concept developed in the Earth project and then follow up in the power model of Green Touch. We have these short D2X frames within OFDM symbols. So the first, the first level of sleep is these sleep on 70 microsecond duration. And we only switch off the power amplifier here. If we can take longer sleeps, if we can switch off or blank a full frame, that will bring us a time frame of 1 millisecond or a radio frame even of 10 milliseconds as a sleep duration. If we can put for, say, for IoT devices, longer sleep durations and wake-up intervals to allow the power amplifier to sleep for longer times. We can go even for longer sleep modes for deep sleep of on the order of seconds, switching off more parts of the base station, even parts of the digital signal processing or the power conversion system. But this requires longer wake-up times to ramp up back all these parts of the system. So we had to build the power model with a detailed understanding of what components can be switched off depending on the duration of the sleep mode and also how much energy is used on the transition between these different states. All of that has been modeled with the lead of IMEC within GreenTouch in designing this parameterized power model for base stations. And it's taking a detailed view of a base station, of the base station type. So if that is a macro base station or a small base station, that relates to the power class. So how many dBm of transmit power, of RF transmit power is the cell emitting? I keep clicking here on the wrong button. So it also adds the feeder loss. Getting rid of the coaxial cable and saving the 50% of RF transmission loss will clearly have an impact on the power model. It's about the bandwidth, if that is a 5 megahertz system or a 100 megahertz system. And further, it also comprises the number of antennas in Mimo systems, from a single antenna to 2 by 2, sorry, or 4 by 4, or even going to extreme cases of Mimo, and I will come to that in a moment. I was showing you the frame structure with the overhead used for signaling and pilots. That is also included into these base station types and the power model, and of course the sleep modes. And all of these different breeds of cell types, for example, shown here on the left for a macro cell, a pico cell, and a massive MIMO cell, will have the scaling rules for the year of deployment. So reflecting the improvement of technology on the path from 2010 to 2015 or 2020, introducing Moore's law in the signal processing, improvements in gallium nitride transmitters, and also changes in the deployment of the network. This power model has been made publicly available. So you can visit it at the website of IMEC. You need to register, and then you can play with the power model, define different types of base stations, and compare them. And I will show you here on the next slide how that looks like. The output of these 3 different base station types. You can see the breakdown, which type of the base station is using power forward part. The macro cell is dominated by the RF power. If you go to small cells or even to massive MIMO antennas with very small RF power per antenna, the dominating part becomes the analog processing of the signals. So this also leads to different scaling rules over time, because Moore's law is different for digital electronics and for analog electronics. You can see that macro base stations have a clear downturn over time, but much larger effects can be achieved for the small cells. So this model can now be applied also for the load dependence of the cells, and I'm sketching here the load dependence for the reference system, the deployed type of equipment in 2010 with a feeder loss, and that is the same curve that you could see on the previous slides. If you are getting rid of the feeder loss and then applying Moore's law improvements for the overall technology by assuming 5% gain annually over the time, we'll reach the green curve here as the expected business as usual design for base stations in 2020. But as I said from the Bell Labs consulting study, it's not enough to do business as usual. We needed to investigate energy efficiency improvement technologies, introducing, for example, the load dependency for transceivers, which drives down the energy consumption, especially in low load situations. And you can see here the clear improvement that we're expecting for a 2020 green design of base stations with the red curve. But also with deployment, we can play introducing smaller cells with less transmit power. We can reduce the maximum transmit power here, and for small cells, then again the power consumption of the cell will be basically flat over the load, because RF is not a relevant factor here. It's more of the signal processing. So these insights gained here for the different base stations, for their scaling with the transmit power and also over time and load, has been used then to analyze the best deployment technologies. Using the plot that you've seen before for the distribution of traffic, we have modeled how the relevant snapshots should look for analyzing the energy efficiency. And we derived this model here with macro cell deployment with a background traffic load. And then within these cells, there is hot zones with much higher traffic density, and then even hot spots with still higher traffic load covered by a single base station. Modeling this, we realized that conventional small cells would not do the job, because at that time, a small base station, was actually just a small version of a macro base station, still running on 150 watt of power for the small cell, not really optimized for low transmit power, running with 4 watt of RF power. What we find here, that small cells actually should be covering smaller areas and running on below 1 watt of transmit power. So using the power model, we find that it is possible to design a brand of small cells that runs on only 7 watt of transmit power, of total power, to deploy for this need of hotspots and hot zones. We can go one step beyond. The benefit for energy in this here is that we offload all the traffic from the hot zones and hotspots from the macro cell to the way more energy efficient small cells. But still a lot of traffic is needed for the macro cells, and the macro cells are designed to provide large scale coverage. By taking an approach to split completely the data and the signal plane, we derived a concept called Beyond Cellular Networks, or Beyond Cellular Green Generation, BCG, where we have designed a complete coverage layer of a large macro cells only designed for signaling for very low capacity, and then a complete coverage of the area with small cells for the data plane. So this may look a bit overdoing it, because it has a real large number of small cells needed to cover the area. But we can see that 5G has taken steps into this direction by designing the step from 4G to 5G, where we have seen the non-standalone definition, where we have the signaling covered in the traditional 4G networks, and then adding a new layer for the 5G data plane only serving data traffic. So that makes this view of Green Touch maybe more realistic, that on the long range we can see this split of technologies. So we've done the number crunching, we've done all the simulations, the performance simulations for these different scenarios, and here's what we found and for the energy efficiency. So recall the number that I was pointing, that the average system at 2010 was running at 170 bits per joule. Dense urban areas were doing a bit better, so that was yielding 0.5 kilobits per joule as the energy efficiency. If we now scale up the traffic 100-fold to 2020 and still run that with the 2010 technology of macro cells, we have a 40-fold increase of energy efficiency just by the scaling effect, by the beneficial scaling of networks when moving from coverage-oriented networks to capacity-limited networks. But still, the energy efficiency is low. It's only 20 kilobits per joule. So by introducing now the green design of macro base stations and adding small cells in this green headnet design, we can find that the energy efficiency scales a factor of 100 compared to 2010 technology, or a factor of 3,600 to the reference system of 2010 with the traffic of 2010. Adding this complete deployment of small cells in the BCG concept brings another factor of 2, bringing up the energy efficiency to 4 megabits per joule. So we can do a big job there for improving from traditional macro cell networks to headnets and improving the energy efficiency. But there are other ways of addressing the energy efficiency, and I was talking about the low load times and the management of cells. So applying energy saving for low load situations, we can address schemes where we completely switch off macro cells. For example, here this middle cell is switched off, and the elevation levels of the other antennas here is increased to stretch the range of the cell and to cover the hole opened up by switching off this macro cell here during night times, for example. The same can be done to small cells. Small cells can be switched on and off according to the need, being the time of day or even specific to the position of the small cell. And that's the tricky part of it. Once you have switched off the small cell, it's hard to understand what users can be served by the small cell. So significant effort is needed on the management plane here to identify when to switch on off these small cells. We can take additional actions, and that is short of switching off a cell completely, twiggling around the capacity of the cell. So the first aspect, we talked about Mimo. So we could switch off several of the Mimo antennas, leaving only one antenna active in times of low need and no traffic need. We can also switch off part of the bandwidth. So having multiple carriers here in times of low load, we can switch off 3 of the 4 carriers and only serve a part of the bandwidth. And the same can be done on the time dimension. Base stations can be put to sleep mode in a part of these on the time. Yet another dimension is indicated already here by the Mimo antennas. So what happens when we switch off antennas? We reduce the capacity and reduce the energy efficiency. So could we go to an extreme and add even more Mimo antennas? And that's a concept followed also in Bell Labs under the lead of Thomas Zeta. And he was introducing a system called Massive Mimo. And I will introduce you here quickly to the idea. Most of you probably will be aware of it, so I will keep it short. Studying the energy efficiency by adding more antennas on the receive and transmitter side, moving from 1 antenna to 4x4 antennas, always improves the energy efficiency over the air, because we have a better signal-to-noise ratio, signal-to-interference ratio, and we have pointing of the energy, directing the energy towards the receiver. This is allows you to adapt the transmit power sent per bit and per antenna. If you increase the transmit power, you can see here this flat area at high transmit power. That is caused by interference between cells, the intercell interference. So there's no need in increasing the transmit power. On the contrary, you can drive down the transmit power per antenna until you reach a spectral efficiency that is just serving the traffic demand that you have in your network. So this is an energy reducing concept, adapting the Mimo scheme by reducing the number of antennas to adjust the spectral efficiency to what you need. But this curve seems to indicate that by adding more antennas, we can simply increase the energy efficiency and the spectral efficiency simultaneously again. But as you guess, this is a simplistic view because this is only looking at the radio reception and the spread of the energy on the air, and it's not following the power model, as I was making a big point for the base stations. So introducing a massive number of antennas, this is the concept of Tomasetta, in having large macro cells with a huge number of antennas in this drum shape orientation would allow to take Mimo to the limit. And that's what Tomasetta actually did. He was studying the limit of infinite number of antennas. And he revealed that this completely changes the interference picture because we are directing the energy using the phase adjustment between the different transmit antennas to direct pencil-like beams towards each of the UEs of the terminals, which increases the energy received at the terminal, and at the same time reduces the interference received from the signals aimed for other terminals. So we have a twofold effect in improving these signal to interference ratio, and that makes the system completely coverage limited. So while traditionally macro cells, at least in high load, are always interference limited, it returns the system into a realm where we are coverage limited, and that drastically reduces the effort needed for managing the resources, for assigning resources to UEs. All the resource management becomes pretty easy because the system is only coverage limited. So how many antennas do we actually need? Tomasetta was looking at this infinite number of antennas. How many antennas are actually close to infinite? Is it 500 antennas or is it 10 antennas? And what will that do to the power consumption? So Green Touch, also with involving Tomasetta here, was analyzing the massive Mimo spectral efficiency, and you can see that with going to hundreds of antennas, actually the spectral efficiency will go up into very large numbers on the order of 30 or 40 bits per second per hertz. But adding the power model, the picture changes. When we add the power model with a detailed modeling of each antenna and the system components, we can see that adding more and more antennas is still increasing the spectral efficiency, but it will have a penalty for the energy efficiency, and we have a sweet spot at a given number of antennas. And it turned out that for dense urban deployments with the traffic pattern of 2020, we found that in dense urban areas, around 90 antennas would do the best job for the energy efficiency. And this clearly depends on the traffic level. So for rural or dense urban areas, we'll have different sweet spots and different number of antennas. Doing the number crunching and using the system level simulations with the power model yielded these numbers here, and it actually shows, as you would probably have expected, when we go to very low traffic, to gain effect from massive Mimo, we need to have a lot of users in every Mimo cell. And that means we need to go to very large cells, stretching out multiple kilometers, and then having a need for a real large number of antennas. Up to 600 antennas have been studied in this area. So the more antennas take effect here for the large cell sites and the few users that we have there, while in dense urban areas, with much less antennas, we can do a much better job and achieve a throughput per site of around 500 megabits per second. Comparing the numbers then between the energy consumption and the throughput, it shows that we have an even better scaling of the energy efficiency of massive Mimo systems compared to the headnet systems that I was showing in the previous approach. And it shows that the energy consumption of a base station site hardly is affected by the range, and the energy efficiency scales with practically directly with the throughput. And this achieves a huge gain of spectral efficiency for a dense urban deployment of massive Mimo, yielding an energy efficiency of nearly 7 megabits per joule, and that is a 14,000 improvement compared with the situation of technology and traffic of 2010 in dense urban areas. So we've done all these simulations and estimations of the different deployment options, and again, also we do the game of playing with the low load situations. This was done after the Green Touch model project already completed by my colleague Hardy Halbauer, also located in Stuttgart, published in 2018 in Globecom. So he was looking at not running the massive MIMO system at the nominal load, but using in times of low load when there are only few UEs. So there's few opportunity in using the multi-user diversity. And what he found is that a muting of the antennas, of a part of the antennas in these low load situations is gaining a lot of efficiency improvement. And he studied different ways to mute, either muting every other antenna or muting a complete part of the antenna panel, and then in even lower load, yet another part of the antenna panel. And it turns out that that is the right strategy to run to these sub panels and gaining overall. So I may have to move my picture here, and to reveal the number of 30% additional gain possible from antenna muting also in massive MIMO. So bringing together all these technologies, we can find that for every situation in the network, we can find an optimum technology. For dense urban areas, it is the massive MIMO technology that offers the largest improvement with 14,000-fold improvement in energy efficiency. While in rural, it's a little less efficient compared to the headnet and beyond cellular approach, where we can achieve gains of 4,000 to 10,000-fold for these lower populated areas. On top of that, we can add more sophisticated use of MIMO by using multi-user MIMO, COM technologies and interference control, adding another factor of, say, 50% on top of the achievements for the BCG concept. So this all piles up into this table of the green meter assessment as the final result of the Green Touch project. We again see the different areas with their snapshot of traffic. We have compared the different technologies from the macrocell technology using 2010 technology, using green technology as business as usual, deploying headnets or the large-scale antenna systems of massive MIMO to find the improvement factors for all these areas, and this piles up into an average of 10,000-fold improvements potential for networks comparing to 2010 reference situation. Then applying the roughly 100-fold increase in traffic, this leaves a factor of 100 in total energy saved. So the 10,000-fold improvement in energy efficiency times a 100-fold increase in traffic is revealing a potential of saving 99% of the energy spent in 2010 for the coverage of LTE systems. So this makes up the point again that I was using earlier as a misconception. Simply observing that traffic is growing does not mean that the energy bill will be growing. There's a lot of potential in even reducing the energy consumption. But as a caveat, I have to mention that this is not something that an operator quickly can adopt, because using these technologies here is actually a complete greenfield approach, doing away with the complete network that was in place and replacing it by the most energy efficient. And the business model of an operator will not allow this amount of investment completely starting from scratch. So it is not to be expected that by today, so 2020, we have reached now this potential of energy saving would be possible to put in place. This will slowly evolve over the time. Green Touch has also looked into other parts of the communication networks. I covered the factor of 10,000 here for the mobile access. We had also groups working on fixed access and the core networks. studying how the traffic increase and the technology progress in these areas would allow to improve the energy efficiency. And they have found much smaller gains, which is not a surprise because, namely, the core networks have always been designed for massive traffic amount. So there's much less potential and also in the deployment structures as we have taken in mobile access. So the gain factors are around 300, and putting it all together in the overall power model of a communication network was then yielding a factor of a 5,000-fold increase, or 89% reduction potential in the energy consumption. All of this has been quite like the power model had this interactive tool that I was sharing with you, has a visualization tool called GWAT, the Global What If Analyzer of Networks, where you can play with different technologies in the access network, for example, adopting massive Mimo in dense urban areas and head nets in rural areas, adding then the BPON network for the fixed access and the core network technology. It will give you a detailed analysis of the performance, both the user performance and also the energy performance of the network. And you can compare different network deployments in this interactive tool. So you can follow this link and play with this tool a bit. Yeah, that completes my journey led by Oswald through the energy efficiency that we can do for the global networks. But we can still keep on going one step further. Again, led by Oswald, as he was the pioneer also of expecting solar energy being a massive source of energy. And so we have come to the term of zero power networking recently. Of course, it is not a perpetuum mobile, so it does not mean the network is running without any power, but it is running the network autonomously without grid power, which is the core of what you're studying in the PAINLESS project. So we can work on feeding the network with renewable energies or with local produced energy instead of grid power. And I like this quite iconic picture here. It actually shows a truck bringing diesel to the power generator of a remote site in a developing country. In the midst of the foliage, there's not even a road, and you need to bring the gasoline here to the base station site. So this shows that there's a large potential, not just for energy consumption, because diesel is not the most efficient way to generate electrical power, but also in the cost of the logistics in providing this power to the sites. So there's a big gain in running solar farms or wind turbines at the site of these base stations to generate local power, and this also reduces the carbon footprint of the network. But connecting this to the PAINLESS approach of small base stations, solar power is not just a benefit for these remote macro sites, but it has a big use for small cells and for moving cells, portable cells, and even in dense urban places. So there is a concept of running small cells with solar power. And we have studied this in Bell Labs in a project called the Future Cell Approach, analyzing the cost. What is the limit? Why don't we see more small cells deployed in the networks today? And it turns out that about 50% of the total cost for deploying networks is in providing backhaul and power lines to the place of the small cell. So bringing the power from the inside of the building with a power meter to the small cell is adding significant cost for the deployment of small cells. So the dream would be to have autonomous small cells that do not need any connectivity, no fiber backhaul and no power feed, rather being connected by wireless backhaul and harvesting energy from solar. This, of course, only makes sense when the size of the solar cell that is needed to run the small cell is in reasonable size compared to the footprint of the device. So we need to go to these low power type of small cells that I was introducing in the power model, running with running below 10 watt of power consumption, to bring the size of the solar cell from what I was showing in this rural place with a solar farm to something that is on the size of the small cell and could even be placed on the hull of the device itself, so needs no extra footprint. And then the second aspect is how do we connect the backhaul? And the approach of Future Cell was to use massive MIMO to direct pencil beams for the backhaul of the small cells, and to make the small cells run as little energy as possible. We designed the small cells to be of relay type, and all the baseband signals processing and the resource assignment of the cells is actually happening at the remote side of the macro base station, and the small cell is more acting as a repeater of this signal. We've built a proof of concept, and this was award-winning for the CTIA of 2016, where we presented first this concept and the hardware concept also behind this, with the modular concept of building up the MIMO panel here. It may have been a bit ahead of the time at that point to claim these relay type of small cells, but when you look at what 5G has been doing in the standardization, we have the concept of integrated access and backhaul, EAB, which allows to provide macro cells with daughter cells and large part of the signal processing being offloaded to the side of the macro cell using the concept of distributed units and central units for the signal processing in 5G. So this is pretty close to the idea that we have here for this Future Cell concept, in having low power small cells with a wireless backhaul and then run by solar cell for the energy consumption. And here also my work touches to what you are aiming for in the PAINLESS project, running portable autonomous small cells. So that concludes my my presentation, the findings that I was taking to you with a stroll with Ostwald through the energy efficiency. So let's recap and sum up, and then close with a call for action for the next decade to work on these zero emission networks of the future. I've presented to you the state of the art of 2010, analyzing the need for energy efficiency improvements to cope with growth of traffic with a 100-fold or even 200-fold growth of traffic expected for 2020. And we have taken the effort to build this concise estimation module, the evaluation module, to build the power model and to derive from that where the potentials are in the deployment, in Moore's law, using Moore's law for the signal processing, analog and digital processing, designing more power efficient models of base stations, and then finding innovative deployments like massive MIMO to keep the energy flat or even have potential to save energy compared to 2010, but with a massively improved performance of the networks of 2020. So that enabled us these innovation and these insights gained in the projects here, led by Earth and Green Touch, made the networks of today still sustainable, so that we can apply and use the capacity of 5G. But on top of that, traffic growth is ongoing, and we have the ambition of further reduction of the energy needed in the networks. IMT 2020 for 5G and beyond has the ambition of improving energy efficiency of 5G on top of LTE by another factor of 100. And on top of that is the increased demand on the signal processing and provisioning of the signal here by having new types of signals. We don't just have the enhanced broadband. This triangle has been mentioned in the introduction of the session. We also have massive machine type communication with very small data volume and very low energy consumption per device. We also have the realm of ultra reliable and low latency communication, which means we cannot afford the most energy efficiency transport, but we have to do this subject to limitation in latency. Ultra reliability means we usually have to do retransmissions or diversity sending from several locations to make sure that at least one copy of the data is arriving in time for the application. So that clearly adds on the energy consumption for these type of services. So this means we need to deal with the new technologies and the new requirements to keep on Oswald's journey to not to waste energy. I would like to sketch here the challenges that I see on this way for the next decade. The first one I mentioned is the new traffic patterns for reliability, for IoT technologies, also for private networks, as mentioned by Federico. We have the trend towards network virtualization, also introduced by Federico in his talk, which means that we are moving functions from dedicated hardware that was designed for performance and energy efficiency to cloud servers with commercial off-the-shelf hardware, also coined as white boxes. So these white boxes play with the ease of deployment, with the mass market available in this hardware not being dedicated for telecommunication purposes, but being off the shelf. But at the same time, it definitely will reduce the energy efficiency and bring higher energy consumption. So we need to model the benefits and the pros and cons of network function virtualization when we move core network functions to a service-based architecture like 5G, and even take one step further and do cloudification of the RAN network and move RAN functions also to cloud servers. A third area of technology progress that needs to be analyzed is millimeter wave. So this will offer extreme large bandwidth for the high traffic demand that we are expecting, but at the same time, this frequency range 2 is calling for completely different technology in the hardware, namely the power amplifier that we managed to bring up from 10% efficiency to 40% efficiency is back to the roots, back to below 10% efficiency in this millimeter wave hardware band. So we will need a lot of work in analyzing how energy efficiency for millimeter wave will kick in and how to improve the efficiency of millimeter wave. Then yet another dimension is massive MIMO with the large antenna arrays and the channel measurement that we need for this. I've shown that massive MIMO has the potential to be energy efficiency, but to further study this and bring this into use, we will need way more work on millimeter wave massive MIMO and the energy efficiency of that. And then finally, I would briefly touch on one aspect, and that is cycling operation. So Leo was showing that networks might not be the ground-based macro cell networks that we are used today, but it may be networks operating in a mesh type of operation between ships and airplanes, or also between cars. So 5G opens this possibility to communicate directly between devices in a multi-hop fashion in cycling operation. But this is now transmitting from user type of devices and not from base station type of devices. And we will have to study how the performance and the energy efficiency of this new kind of traffic transportation in networks will evolve. So all of these challenges will again have to be studied holistically, like we did with our evaluation framework, studying power models, studying deployment models, studying traffic models, and we will need experts of all these areas, hardware, signal processing, deployment, and traffic models to work together to model these systems end to end, and to avoid running again into these misconceptions that I was presenting at the beginning of my talk, because that would yield to the wrong direction and wrong results. Do we think that these technologies will be deployed? I've shown you the multiple times of disappointment or disillusion for the deployment of energy efficiency. But I'm very optimistic that now we are approaching the plateau of productivity for efficient networks. And my hope here is that actually, since 2010, when we did not manage to bring in binding agreements for global stopping global warming, in the Paris Agreement, we have taken a step ahead. We have decided that we need to limit the energy, the temperature growth even below 2 degrees to 1.5 degrees to prevent excessive cost in catastrophic change in the climate. And countries are digging into binding agreements here, and also the industry is picking up this ambition to now follow this call for reducing energy, not just for the sake of cost, but also for the sake of the planet. And interestingly, right in this year, in February, end of February, the leading players in our industry, GSMA, ITU, and GESI for the energy efficiency, have led an initiative to roll out a trajectory roadmap for the ICT area, breaking this down for each sector for the roadmap from 2020 to 2030. And for mobile network operators, they claim that to do our share on following the science insight in climate warming, this is called the science-based target (SBT) approach. To do our share as industry, we need to reduce our carbon emissions in this decade by 45%. And taking one step further, until 2050, the market needs to get to this net zero carbon emission, which is pretty much close to the zero network ambition that we were just discussing also for the PAINLESS network project. So we can see that there is a movement in the industry to accept energy efficiency as a roadmap for the next decade. And a large deal of these carbon dioxide saving will go to the use of renewable and low carbon electricity in the network, but it will also expect the operators to run every method that they can use for energy efficiency. Within 2 months or since the announcement of this roadmap, 29 of the large leading operators have presented their individual goals to follow this roadmap to reduce their carbon footprint by 30% and in the end become carbon neutral. Some even committed to become carbon neutral way before 2050 within the time frame of 2030. So we can see this movement that there is a need for this technology, there's a will to deploy this technology, and so this should be a motivation for us as the research community to deal with this energy efficiency for the next decade, addressing the challenges I was presenting in the 5G technology and bringing higher performance and bridging that also with energy efficiency improvements on the further increase of traffic in the next decade and working in standardization and providing products to roll out these energy efficient networks. And that will enable us to keep networks sustainable, to follow Ostwald, not to waste energy, so that we can harvest the potential of 5G networks, the social economical potential, and also the abatement effects by running more service wireless and in remote operation, replacing physical action by digital action, digitizing economy, and doing and earning the leveraging effects of this. So this is my call for action for you as the upcoming researchers in this field. So I will close again with a poll here to take your feedback from how you feel about energy efficiency with a full range of opinions that you can take here, starting from the climate neglectors saying that all of this is a hoax and we should not throttle our economy for caring for the extra cost for energy efficiency, towards something that is energy efficiency well understood by now, also contributed by the work that I was presenting here from the projects. But now we have done our deal and energy efficiency has reached a limit. Or the final opinion would be that this is still opening challenges and improvement, and that you would decide to devote at least a part of your career in dealing with energy efficiency. So thanks for your attention. I will be open for some questions if we have some time left. I think I've gone a bit over my limit already. I would just mention that I have some references here in my slide set, and also credits to my co-workers in the Bell Labs and in the projects that I've been citing. So open for your questions.
Yeah. Thanks a lot, Oliver. This was really a fantastic seminar. Like we received already a few questions, and yeah, thanks a lot for putting together as well the reference, because I'm sure that for our students will be very useful. So regarding the question, there was a question from Marco. Are you connected? Can you talk? Yeah. Okay.
Hello.
Yeah. Hi. So yeah, go ahead, please.
Hello, Oliver. First of all, thank you, and for the whole presentation, and for the my questions mainly regarding one of the misconceptions, the one regarding the bandwidth, the communication efficiency versus energy efficiency, which was number 3 or 4, I don't remember now. Yeah, it should be slide number 21. The third misconception.
Okay, this one.
This
okay.
one.
Go ahead.
Number 3. Yeah. So as far as understood, the more dense the base stations are deployed, the lower energy efficiency you can reach. But doesn't this mean that with the advancement of telecommunications, the energy efficiency is doomed to get worse and worse with time? Because for example, 5G requires a much higher density of deployment, and 6G probably will require an even higher density. So it would go further and further right on the x-axis.
Okay, I see your point. The misconception I was presenting here is that small cells, not per se, are the most energy efficient way. We need to study the power model, also understanding how the power consumption is depending on the load, and having a small offset will penalize very small cells. But also it's clear we need to design the network to capacity. So we have to find the right balance. This is what I call the sweet spot between the capacity need. So how many cells do I need to serve this capacity? And then balance this with the power model of the cells. We also see a lot of potential then in the power model. So for example, we have seen the improvement in the power amplifier efficiency, but we have also seen the large improvements in the signal processing, for example. So this offset of 10 watts that I was proposing here, that would cover the signal processing, and we have benefits or improvements here with Moore's law when the 7 nanometer technology or even 9 nanometer technology would offer a lot of energy efficiency gains for the chipsets. So I think this is a game that we need to play with the technology improvement, with the growing demand for traffic to find the best densification of the networks.
Okay, thank you.
Marco, do you have you were writing another question in the Q&A. If you want, you can ask as well another one. Then we pass to the other attendees that he wants to ask another question.
What I asked is just a reformulation of what I wrote on the Q&A.
Okay.
It was the same question. Thank you.
Okay, good.
Thank you.
Okay, so now there is Albert. Hello, Albert.
Hello, can you hear me?
Yeah, yes, perfect.
Okay, excellent. So hello everyone, Konstantinos, hello especially. Okay, my first question is, on this very slide, you have path loss exponent proportional to the force power of the distance.
Yeah.
My assumption it is valid for urban areas. And yes, for rural areas, it's not really valid. And then this plot is going to look different. Has this been taken into account in the slides which you showed after this?
Yes, of course. So I was simplifying the picture here to make the point and to get you to understand this. But actually, we were doing the simulations in 3GPP compliant system level simulators that have these complex path loss behaviors for the different areas, for dense urban and for rural. We've really taken the radio performance and then combining this with a power model into this overall energy consumption in the framework. It was just for this introductory slide of the misconception that I was taking this very simplistic path loss coefficient.
Okay, thank you very much. It's a very impressive presentation, I must add, because it's very comprehensive and looks probably 10, 20 years ahead at least. Okay, if I may ask, Lorenzo, if I may ask second question.
Yeah, sure, go ahead.
Okay. Have in those models, have you considered the uplink, downlink decoupling?
You mean in FDD systems?
Yeah, when the downlink is done using higher frequencies, where you can have higher bandwidth and so on, and you can afford higher loss because your power from the base station is higher. And uplink is done using lower frequencies.
Yeah, conceptually that is covered by this framework, but in the simulations we were not really doing a large split there into two different carriers. This is something that might be added in 5G technology with separating this completely, but I don't think it is completely changing the picture. It may have some additional opportunity to play with an optimizing of the networks for the split between uplink and downlink traffic. If that is not symmetric, you can design uplink and downlink direction for highest energy efficiency separately.
Okay, sure. No, I agree with you. So from numbers I saw where they were gaining about 8 decibel in the budget, which means they were probably doubling the distance by doing that. But your BCG approach is simply brilliant. All right, thank you very much. That's all questions for me for now. Thank you.
Yeah, and if you want to go for more details here, I would direct you to these presentations. We have the final presentations of the Green Touch Green Meter. We have this seminal presentation there of Earth, and you will find way more details there to dig into the numbers.
Brilliant, thank you.
Yes, there is another question from Tetskan. I will ask you directly the question because we have some audio problem, I think. So yeah, the question is about if you are aware of any practical of any study that practically makes adaptive sleep mode in a self-organized way. So
the way we thought of it was actually also self-organizing in the way that we have a feedback between the baseband processing and the power amplifier. So from that, during scheduling, you already know when your power amplifier will be needed and when you can take sleep modes. So there's inside the base station a possibility to have this interface between cross-layer interface to achieve these gains from adapting the power amplifier. But I think your question was aiming in a bit of a different direction using machine learning aspects. What were you aiming at?
I don't know. Let's see if he replies in the chat. Yes, he said yes. So,
yeah.
No, it was not me asking the question, Oliver. I was just reading the question from one of the attendees.
Yeah, I think that is a valid question, a very recent question that many of the deterministic algorithms that we used to apply in networks are being replaced by machine learning, by pattern recognition to find the optimal configuration of the network. So I definitely think that this will be the way for 5G and beyond to to be even more fine granular. And I would see a potential, namely for the massive Mimo, where you need to find the pairing between users and finding the best beam selection and beam forming. So that is something that might be more reasonable to do with machine learning and pattern learning instead of finding fully deterministic algorithms.
Christos, do we have time for another question?
I'd like to ask one if we have a bit of time.
Okay, because there is another attendee that wants to have a question, but yeah, you can go ahead and then go ahead.
So I mean, thanks again, Oliver. I think you make a compelling case for energy efficiency. Even if some of us were not convinced, you won't find many of us in Painless, by the way, that are not convinced. But you still, you make sense. It makes sense, your pitch for energy efficiency. But I wanted to ask, going one step further towards this zero energy operation, or what we call the energy autonomy operation. So here we have, I see this as slightly different. So an energy autonomous network is not necessarily energy efficient, and an energy efficient network is not necessarily energy autonomous. So maybe there's a case where there's a case for sending a drone somewhere to serve a network which is not the energy efficient way, but maybe it's the only enabling way. And to measure that would require new metrics, I guess. So I wanted your opinion on this topic, on the energy autonomy, and whether you have, you can contribute, or you have some ideas in terms of metrics, performance metrics for this zero energy network that you call.
I think you already gave the answer yourself. It's all about the metrics. So I think the framework is a way of addressing the comprehensive view of a complete network. And that was really opening new doors to add these snapshots of representative chunks of the network into the overall picture to identify what areas of the network are eating up the energy and where's the potential of improving it. But in the end, you can stitch in other metrics there. We were aiming this for energy efficiency, but you might use this also for maximizing the performance or for having a constraint on the availability of energy. And the example that you were giving for drones, there is a limited, it's not then about the cost of energy or the availability or the carbon footprint. It's really the only way to make the performance. So that's a requirement then. I was touching this a bit already in my presentation with this chart here, where I mentioned the size of the solar cell relative to the cell. So I think that the game that we need to play is make the energy consumption of the base station on the drone so small that we can harvest enough energy to feed this. So it's the way that also 3GPP is taking and shifting around functionalities and moving functionality where energy is easily available, or also where processing power is more easily available. So I think it's all in the framework, and the metrics will define what architectures are preferred and how to develop then the system.
Okay, one last question. Richard, you would like to pose your question? Richard? Hello? Hello? No. Okay. So we have another question.
Yeah.
We have a last one.
A missed opportunity, someone else stepping in.
Yes. So Mashid is asking if there are any reference modeling for the power consumption of the 5G case, if you know.
No, I'm not aware of that, and that is exactly what I was calling for in my challenges. We have done this work until, say, 2015, studying the performance of LTE, basically. I think the approach still holds, but it needs to be extended. And I was sketching here these different areas, namely millimeter wave. I see as a big pain where the efficiency of the hardware is very low today, and we need to see how far we can go there to make this more energy efficient. the other area with the network function virtualization. This is a very strong market drive by the flexibility and the speed of deployment for the operators. So this is not driven by energy efficiency. And we need to understand if that is detrimental, or if it moves in the same direction, that we can also be more energy efficient when using these new trends of softwareization. But I fully agree to you that we need to keep on researching here, refining the research questions and adding these new technologies and approaches to the power model and to the framework to understand what's going on in 5G and beyond, to make sure that we are not developing 6G in a way that will not be sustainable.
Okay, I think we can leave it here. Many questions. If you have further questions, feel free to reach out. I think, Oliver, we will share your presentation, so I think there should be the email address as well, so in case you...
Yeah, it's also in my slide set here, so feel free to reach out to me. I hope we'll be able to deal with all your questions.
Yeah. So with this, I think we can close it here. So thanks again, Oliver. Very interesting, and thanks again as well, because today is holiday in Germany, so you also dedicated these days to be here with us.
Yeah, thanks you for listening and for the good questions.
Yeah. So Christos, to you. No.
Yeah, thanks again, Oliver. And I think we're ready for a bit of a lunch